Hi guys, welcome to this video. I'll be going through the AS paper, Breath in Physics, of the 2024 exam series. So let's get started with the first multiple choice question. Which is an SI base unit? There are 7 SI base units and amps is one of them, so A is the answer. Remember that coulombs is a derived unit and so is ohms and volts. Question number 2. Two waves of wavelength lambda undergo constructive interference. What is the possible path difference between the two waves? If it is constructive interference, then it has to be whole multiples of lambda, and therefore D is the most straightforward answer there. Question number 3. We have a copper wire, P, which has an electrical resistance of R and the number density of charge carriers is N. And we have another copper wire, Q, which has an area of cross-section equal to that of P and twice the length of P. Which row gives the correct value of resistance and the number density of the charge carriers for Q? So we know that the resistance is dependent on, the formula is rho L over A. Now because obviously both of them are copper wires, resistivity is going to be the same, and the length and area is what resistance depends on. So if you have got the area of cross-section equal to P and twice the length of P, then the resistance of Q will therefore be 2R, and the number density will be the same as P because it is still the copper wire. So therefore C will be the answer here. Question number 4, it says that the light emitted by a laptop screen is polarized. The laptop screen is viewed through a polarizing filter. Initially, the brightness of the screen appears normal, and the filter is gradually rotated through an angle of 180 degrees. How does the brightness of the laptop screen appear after the filter has been rotated, first by 90 degrees and then by 180 degrees? So if you rotate it by 90 degrees, it will become dark. And then if you go by another 90, so basically making an angle of 180, it will go back to normal. So B is the correct option here. Question number 5. We've got the diagram below which shows a network of 4 resistors. And here we've got 2 resistors in series and another 2 resistors in series again, and then the total is connected in parallel. We have 200 ohms of resistance as well as 400 ohms of resistance. What is the total resistance? That follows the formula of 200 times 400 over 200 plus 400, which gives me. Then we've got question number 6, which shows a stationary wave on a string. What is the phase difference between the points labeled X and Y? So they seem to be pi radians away from each other, so D will be the answer. Question number 7. We have, in a demonstration of photoelectric effect, the clean surface of a metal is radiated with photons of electromagnetic radiation. Electrons are released from the surface of the metal and the intensity of the radiation is then increased. Remember that with intensity, current increases. Therefore, the rate of emission of electrons will increase. So B will be the answer. Question number 8. Electromagnetic waves pass through a gap of approximately 3 centimeters, so 0.03 meters. Which of the following will undergo a significant amount of diffraction? Diffraction is significant if the wavelength of particular radiation is the same as the gap width. Microwaves are the closest to it, so therefore A will be the answer. Question number 9. According to Newton's third law, forces always act in pair. Which statement is not true for it? The forces are acting on 2 different bodies, so therefore B will be the incorrect statement here. Question number 10. A particle X collides with a stationary particle Y, no external forces act, and the collision is inelastic. So we know that the kinetic energy is not conserved. Which quantity is conserved? It is the momentum of X and Y. So C will be the answer. Question number 11. We've got some diagrams where the currents are in and out of the junction. which one is the correct option. We've got 6 amps over here and 6 amps over out as well, so D will be the answer. Question number 12. In the Young double slit experiment, light passes through 2 narrow slits and a pattern of light is observed on a screen. Which property of light is not demonstrated by this experiment? It would be refraction. That's not part of this experiment because refraction is based on light traveling through different media and changing the speed. Over here, it shows all these phenomena but refraction, so B is the answer. Question number 13. In a Young double slit experiment, electromagnetic radiation is incident on a double slit, and we've been given a bunch of values. So we've been given the distance between the slit and the screen, so we've been given the value of D, the distance between the central fringe and the 6th order fringe. So what they mean is basically if you had a central fringe and then you had 1, 2, 3, 4, 5, 6. So the distance between here is 9 millimeters. It's asking us to calculate the wavelength, and we know that wavelength is AX over D, where X is the distance between the 2 fringes. And this 9 millimeters divided by 1, 2, 3, 4, 5, 6, so 6, and that is 1.5 millimeters. So watch out for that, okay? And therefore, when I insert these values, I'm going to have 1.5 millimeters by 1.5 millimeters, again, so squared, I guess, 10 to the minus 6 to convert it into meters, and divided by 3.5, and that will give me result of A, 6.4 times 10 to the minus 7 meters. Let's move on to question number 14. So we've been given a stationary sound wave created in air, and the distance between 2 adjacent nodes is 0.7. The distance between 2 adjacent nodes is lambda over 2, or half a lambda. Therefore, lambda is 1.4 meters. One can find out the frequency by using the wave speed equation, so 340 divided by 1.4, or simply 243 hertz. So A is the answer. Right, question number 15. So we've been given a spring which has a force constant of 4900 Newton per meter, and a force is applied to the spring causing it to compress. That means its elastic potential energy is increasing. And what is the change in the elastic potential energy stored in the spring? We can work that out quite easily. So we know it's either C or D. So half times 4900 times 0.5 squared. And that gives me C as the answer. Question number 16. Which graph shows the stress-strain characteristics of a brittle material? Remember, brittle material is something that breaks quite easily has very little elastic region and basically no plastic region. The best case scenario here will be A. Even if we had a little tip to show the elastic region, it can have it. Very little. That would have been an acceptable answer, but none of the other options match because they have very high plastic regions. So I'm going to go for A as my answer. All right, question number 17. We have to give the correct statement about the EMF of a cell. Everyone should know the definition of EMF, and it is basically equal to the potential difference measured across the terminals of a cell when there is no current. It could also be said as the amount of chemical energy transferred into electrical energy as the electrons move across the terminals. The best option that fits the definition is D. Okay, so D is the answer. Question number 18. We've been given a diagram showing a semicircular glass block with a refractive index of 1.5. The glass block is surrounded by air, so we know that N is 1. And a ray of light follows the path shown from X to P. Which path will the ray follow after it arrives at P? We should work out the critical angle first here to see whether total internal reflection is happening or isn't. C is where C is the critical angle. sine inverse of 1 over 1.5, and that gives me 41.8 degrees. And clearly, the angle of incidence here is greater than that. So total internal reflection will occur, and it will follow the path of A. A is the answer here. Question number 19. A student makes measurements to determine the total energy transferred by a filament lamp. They record the following measurements. What is the percentage uncertainty in the calculated value of W? So we know that W, or energy, is power times time, and therefore it is I times V times T. So we just need to work out the percentage uncertainties in all of them and then add them together. So it will be just 1 over 80 plus 0.2 over 12 plus 0.01 over 60, all times by 100, and that would give me C as the answer. Question number 20. An object is completely immersed in water. Upthrust acts on the object, and which calculation will correctly give me the magnitude of the upthrust? We know that upthrust is equal to the weight of the object, which is equal to m times g, or the mass of the water displaced times by the gravity. So C is the answer. Let's move on to section B now. Question number 21 states that a torch uses 3 identical cells connected in series to a bulb. Each cell has an EMF and internal resistance of R, and the current in the circuit is I. We need to show that the power delivered to the bulb is given by this equation here. Okay, so let's start with the most basic. We know that power is equal to current times voltage, and we know that voltage, or EMF, is V plus I times R, or V in general can be written like. And because you've got 3 cells connected in series, you're going to have 3 times the EMF, there you go, and it will have 3 times the internal resistance as well, so I times 3R. In other words, I can just take a factor of 3 out, and I'm going to have something along these lines. And that can be then inputted into my equation here, where the current obviously is just as is, and the 3 comes out, and V is EMF minus I times R. That's easy peasy question 21A. Let's move on to part B. It seems a bit too easy for 3 marks, but I'll take it. Suggest why a torch battery with a large internal resistance may be undesirable. Okay, so if we have, so let's just go back here. So if you have a larger internal resistance, you're going to have more volts per unit current lost, right? So the larger the value of R, the more volts will be lost per unit current. And this means that less power or potential difference will be delivered to, or available to the bulb. Hence, it's not ideal. Question 22. A lab technician is moving boxes. The technician pulls a box using a rope with a force of 32 newtons. The force acts at an angle of 50 degrees to the horizontal, and the box moves a horizontal distance of 3.5 meters along the floor in 6 seconds. Calculate the power of the technician as they move the box along the floor. So we know that power is associated with force and velocity. And we know that this has a component of the force along the horizontal. So that is the component that will be used over here. So 32 cos 50 times by the velocity, horizontal distance of 3.5 meters in 6 seconds. So that would be very straightforward, and it will give me 12 watts as the answer. Okay, part B. The technician lifts a box from the floor without bending their knees. The diagram shows the force W due to the weight of the box. Okay. And the box has a mass of 5 kilos. The distance D is 0.6 meters and can be assumed to remain constant. Calculate the moment about the point H due to the weight of the box when theta is 90. That means the person's back is basically at this angle, and that's 90. the distance remains constant, so that's good to know. We know that moment is equal to the force times distance, and 5 kilos times 9.81, the distance is 0.6, which gives 29 Newton meter. Part C. The diagrams show how the technician can pick up the boxes whilst bending their knees. This keeps their spine more vertical. Explain why bending the knees is less likely to cause damage to the spine. Okay, so if you bend the knees, you're basically reducing the perpendicular distance, okay, which is essentially reducing the moment and also reducing the impact, the force. Question number 23. A thermistor has a resistance that decreases as the temperature increases. A student makes measurements to plot the variation of resistance with temperature of the thermistor. They submerge the thermistor into distilled water at 50 degrees, and then they record measurements from a voltmeter and an ammeter as the temperature of the water falls to about 20 degrees Celsius. Describe how the student obtains sufficient data to plot a graph of resistance against temperature, and you should include a circuit diagram, and this is for 4 marks. Okay, so let's start with the circuit diagram. We can have a cell, an ammeter, a thermistor, and a voltmeter. So there we go. Students should record the temperature, obviously with a thermometer, at, let's say, intervals of 2 to 3 degrees Celsius to get about 10 readings of current and voltage. Then you can calculate the value of R using V over I. The student should also repeat the experiment to get an average value of R and then plot that value of R against the temperature. What the student would see is an exponential decrease of the resistance with respect to the temperature. Part B. The circuit diagram shows a potential divider circuit using a thermistor to detect changes in temperature. The LED switches on to indicate when the temperature is above 30 degrees Celsius. We've been given the variation of the resistance of the thermistor with respect to temperature. Explain why the LED will switch on when the temperature of the thermistor is above 30 degrees Celsius, assuming that the resistance of the LED is always much greater than 55 ohms. Okie doke. Let's just look at the diagram first. So, first of all, when we look at 30 degrees Celsius, we know that the resistance across the thermistor is 30 ohms. Okay, so 30 ohms. Now, remember, and as per the graph as well, the resistance decreases with temperature. So, if the resistance across the thermistor decreases, voltage also decreases across it. Therefore, more volts will be available to this fixed resistor over here and the LED as well, which is connected in parallel. We are expecting, if the temperature is above 30 degrees, then the voltage will be higher across. Now, we just need to put some numbers in. So we know that V out is equal to R2, which we know it's 55 and above across the LED, and 55 plus 30 ohms, and times by the V in, so 5 volts. And that would give me a value of 3.2 volts. Going back to our diagram here, we know that the threshold frequency for the LED to work is 3 volts. So obviously it's going to work because 3.2 is greater than 3 volts. I'm going to write this up and put a link in the description box so you can look at the written solution. Question number 24. A student investigates the motion of falling objects. The student releases a feather in air and allows it to fall. The feather reaches a terminal velocity. Explain this observation. We know that when the air resistance acting on the feather equals the weight of the feather, the resultant force acting on the feather will be 0. which means it stops accelerating and reaches a constant speed. And that's what terminal velocity is. Okay, part B. The student now releases a heavy ball and allows it to fall from a height of 2 meters. Calculate its expected speed when it hits the ground. Assume the air resistance is negligible. V is what we're trying to find, and A is 9.81. V squared is equal to U squared plus 2AS, which means that V is square root of 2 times 9.81 times by 2. That gives me a value of 6.3 meters per second. Part C. The student measures the time for the heavy ball to fall from a height of 2 meters. They release the ball and at the same time start a stopwatch. They stop the stopwatch when the ball hits the floor. These are the measurements. Calculate a value for G using the student's results. Let's get the average first. Doesn't look like it has any anomaly. Add them all up, divide by 3, which gives me a value of 0.63 seconds. Then just use, again, S equals UT plus half AT squared, or GT squared, where G is 2 times S over T squared, as U is 0. That is going to give me a value of 9.97 meters per second squared. Suggest one improvement the student could make to the investigation described. Bunch of things you could improve, really. You could use a larger height to reduce the uncertainty in time, or you can also use light gates with data logger to record the time. All this will basically remove random errors in time, thereby reducing the uncertainty. The ball bounces when it hits the floor. On the axis below, sketch a graph of height against time to represent the motion of the ball from t equals 0 to t equals max when it reaches its maximum height after hitting the floor. Now, given that there is no effect of air resistance, it will reach the same height. And we know that S is basically equal to half gt squared. In other words, that S, or height, is proportional to t squared. We know it will be a curve and very symmetrical, so let's move on to our next question. Einstein's photoelectric equation can be used to explain the photoelectric effect and what is meant by Ke max. It is the energy with which the photoelectrons are released from the metal surface after they gain the energy from the photons in that one-to-one interaction, and as long as this energy exceeds the work function of the metal. All right, so that's that. Part B. The photoelectric effect can be demonstrated using a gold leaf electroscope, and electroscope consists of a metal plate attached to a metal rod. A thin gold leaf is attached to the metal rod. When the electroscope is charged, the leaf rises. Initially, the electroscope has an excess of electrons and is negatively charged, and the leaf rises to the position shown below. Electromagnetic radiation is then directed at the metal plate. The leaf falls to the position, and we need to explain this observation. As the EM radiation causes the photoelectrons to be released from the metal plate in, again, one-to-one interaction with the photons, because what happens is one electron gains one photon, okay, and thereby gains the energy of it. Therefore, the leaf will become less negatively charged or slightly positively charged, so it'll be attracted or it will fall back to the metal rod. Okay, so that's basically how it would work. Part C. The investigation is repeated using the electromagnetic radiation with a frequency lower than the threshold frequency, and the leaf does not fall. Explain why. That's because for the photoelectrons to be released, the frequency of the photons, which are incident, must exceed the work function of the metal. Okay, next question, number 26. A student carries out an investigation to determine the value of Planck constant, H, and they use the following circuits. Okay, initially the LED emits no light, and the student increases the potential difference across the LED. They record the potential difference on the voltmeter when the LED just starts to emit light. The measurement is then repeated for LEDs that emit light with different frequencies, and the student views the LED through a cardboard tube when making each measurement. Explain how this can help to improve the accuracy. This will basically, so if you use a cardboard tube, it would ensure that the path of the light which is being emitted by the LED is more concentrated and it's not spreading through the room, right? It's making it concentrated and narrow, which is going to make easier for the student to make a clear observation when the LED is just turned on. You can also say that it removes any ambient or any background lights in the room and prevent you from identifying the LED light that is being emitted. Part B. The student plots a graph of V against F. Calculate a value of the Planck constant using this graph. Well, if you just look at the most basic equation of photoelectric effect and then manipulate it in such a way that we can actually apply it to this question. So we are dealing with voltage and frequency. If I just wrote down the EK max as equal to EV, which is the charge on the electron times the voltage, then we can say that V is equal to H over E times by F, okay, minus the work function phi over E, right? So this is now in the form of Y equals mx plus c. And we're only interested in the gradient. But let's work this out and see what we get as a value. We have that value right here, and it will be 1.52. And okay, that's just be careful about this humongous power. So the gradient is going to be 1.52 minus 0 over 7 times 10 to the 14 minus 0, which gives me a value of 2.17 times 10 to the minus 15. That's the value of the gradient, which is equal to h over e. This means that h is the gradient times the value of E, which is the charge on the electron. That ends up giving me 3.47 times 10 to the minus 34 joules second. It is within the same power. It's definitely off, but that's just experimental error. So an accepted value is that. Calculate the percentage uncertainty. That's easy. So that would be the difference between the two over the original value, which is again, and that gives me quite a significant uncertainty of 48%. Okay, let's move on to part D. One of the LED emits red light, another of the LEDs emit blue light. And the red LED emits these many photons per second, blue LED emits light with frequency of this much. The manufacturer lists the power rating of each of the LED as 1 milliwatts, and the student states that there are more photons emitted per second from the blue LED than the red LED. Deduce by calculation whether the student is correct. Okay, so let's talk about the blue LED, and also let's then compare the number of photons emitted, because we've been given the number of photons for the red LED, right? We know, so for blue LED, E equals HF, and I'm just going to introduce power. So power is equal to, I'm just going to say n number of photons over T, okay, times by HF, right? So if you don't know this, then I would say remember that power equals energy over time. Now, what I want is n over t value, right? So therefore, n over t, or number of photons emitted per second, is the power over hf, which is really simple, because that's 1 milliwatts, so that's going to be 10 to the minus 3, 6.63 times 10 to the minus 34, times the frequency, which is 6.38 times 10 to the 14 hertz. And that gives me a value of 2.4 times 10 to the 15. Comparing this value to the one of red LED shows that the student is therefore incorrect. So student is incorrect, and that's basically that. I hope you found this walkthrough useful. Do leave any comments if you have any questions. Overall, this paper wasn't difficult compared to some of the other papers in the past, but with a few exceptions, obviously. I will see you guys in the next paper, and thanks ever so much for watching.